Good morning, and I'll try and give you a little bit of an overview on, what Tesla, is and what we're doing and what we have done, and also a little window into where we see the future of electric vehicles and how that can play a part in the entire sustainability and energy efficiency puzzle, because transportation energy use is a key part of that, and it's a particularly tricky one to attack, sometimes a little bit harder, I think, than stationary challenges. So, for those of you that don't know Tesla Motors, I'll give you a second on who we are and what we are. We're a relatively new company, about 8 years old. I'd almost still consider us a startup company, and we're a U.S. manufacturer of electric vehicles. We kind of developed from the inside out, focusing mainly on powertrain technologies and on all the systems needed to make an electric vehicle work. So batteries and motors and power electronics, and have grown sequentially, building a vehicle brand and now building vehicle manufacturing capability. We have a product that's been in the market for several years now, a Tesla Roadster sports car, very high performance electric sports car. We have about 1,200 people. We're a public company now as of last year. And this is something where today we have a pretty broad reach. We're not just selling cars in California. A lot of people think that. We're actually selling vehicles around the world and have Roadsters in over 35 countries and stores around the world. And actually Europe is now a larger sales draw than North America, in fact. So that's just a quick overview on us. And the first, just a little bit more about the Roadster. Maybe some of you have seen this product, but it was really conceived of to be something that would be a technology demonstration in some ways, and to kind of throw down the gauntlet and change stereotypes on what electric vehicle technology could do. And we didn't do this because we thought the world needed another fast sports car, but we wanted very much to dispel the stereotype that electric vehicles had to be golf carts or neighborhood electric vehicles. And this car can compete head-to-head with gasoline cars in the same price and performance range. And I think really can prove that the technology has come quite a bit further and doesn't need the same level of subsidies or handicaps or limited markets that people might expect. This is the next vehicle that we're currently working on. This is where most of our R&D efforts go today, and it's a luxury performance sedan, enormous amount of cargo capability, and also embodies a second-generation powertrain. So we've spent a lot of R&D time focusing on how to improve the powertrain and reduce cost. And I think the biggest challenge facing alternative transportation today is cost. The technology has actually come fairly far in the world, and we can get range and performance that's quite compelling, but driving the cost point down is what will really increase adoption. And like I said, Tesla wasn't founded because we thought the world needed more cars or needed more performance cars or more sports cars. But a lot of us in the beginning were very driven by this kind of high-level challenge that I see anyway of how do we transition our entire economy, all the different aspects of it, from fossil fuel use to sustainable energy use. And I think it embodies so many opportunities and so many companies that need to get started that it's really pretty exciting. And it's going to be with us for decades and decades as we kind of make this transition in all different aspects. But this was really one of the big opportunities that we saw coming. And 8 or 9 years ago, alternative transportation, electric vehicles were absolutely not on the radar screen. Oil was at all-time lows 8 years ago, and every investor we tried to talk to pretty much laughed us out of the room and said, "This is nuts. Why are you guys thinking of alternatives to oil? It's incredibly cheap. This isn't a problem." So I guess today it's a little bit more in people's minds, but I think it's still not as prevalent as it needs to be. And I sort of encourage everyone to sort of have those arguments and discussions whenever it feels like efficiency might not be quite the right answer yet, or an alternative technology might not be quite the answer yet. They will be more relevant soon. And kind of drilling in on what is our key mission, we're really focused on converting transportation energy use to electricity. That's kind of the fundamental premise that drives us, and we have a couple different business models that go after this, but most of them revolve around technology. And fundamentally, this is a technology problem. It's not for lack of better styling or for better cargo space or things like that. It's for lack of better integrated powertrains, better battery systems, better software and controls, and those are the problems that we tackle and where we develop intellectual property. And I think that is very much the roadmap on where improvements are going to be coming. All of these diverse areas. We also leverage a lot of that R&D and sell that to other customers. So today, Tesla licenses or builds products directly for companies as diverse as Smart. We build battery packs and charging systems for all the electric smart cars that are out there, and a Mercedes electric A-Class, a Toyota RAV4 that's coming up, and Freightliner trucks. So it's a pretty broad set of technologies that we're enabling behind the scenes. And maybe just take a second to think about, is this really the right direction to be pushing? There's a lot of hype and a lot of excitement in the market about it today, and less so a few years ago. But we thought really long and hard before spending so much time and money and effort on electric vehicles to think, is this scalable? Is it something that really has the fundamentals to be a meaningful solution? And I think the analogy about corn ethanol is a good one. That's a case where I think if you really look at the fundamentals and be honest, it is kind of a difficult solution. It doesn't make all that much sense in some cases. And I think electric vehicles have a much broader set of support and can actually be a much more scalable solution. And I think I would break this down into really two main categories, even though there's a couple points here. One of them derives from the fact that when you have a plug-in vehicle of any type, whether it's a plug-in hybrid, a range extender, or a pure electric vehicle, you can get your energy, your primary energy to drive that vehicle from a bunch of different sources. It comes from whatever the electricity was generated from. So you're fundamentally decoupled from petroleum and decoupled from oil, which is one of the hardest problems in tackling transportation energy, is decoupling those two, petroleum from the transportation energy use. And by definition, it's domestic. You're not importing electricity over oceans or something like that. It might come across a continent, but it won't come across an ocean. So it really fosters local investment and local trade balance. And then the second set of benefits come from efficiency. Electric vehicles and electric powertrains have some fundamental reasons why they're just more efficient, thermodynamically more efficient than a combustion powertrain in a vehicle. And a lot of this comes from the fact that electricity, when you store it in a battery, is a very high-quality type of energy. You can convert that into motion and use an electric motor to drive the wheels and do it with very high efficiency, not very many losses, and get back basically all of the energy that you put into the car for useful motion. So, for example, the electric powertrain in our vehicles is about 85% efficient. So, end to end, all the energy that you put in to charge it, about 85% of that comes back out to the wheels to actually move the cars around. Internal combustion engines, might be somewhere in the 15 to 25% average range, and typically closer to 15 over realistic drive cycles, where 15% of the chemical energy you put into the car actually goes into useful mechanical energy to move you around. So that's a pretty huge difference. And certainly it's not the whole puzzle, because you had to make the electricity somehow. But generally, making electricity in central plants or from different sources is far more efficient than trying to make it in a lot of distributed, very small engines that are ramping up and down depending on what people are doing with their accelerator pedals. So in that way, electric vehicles offer a dramatic increase in efficiency and a reduction in just primary energy per mile needed to move a whole fleet of cars. And that'll be helpful as we continue to try and move toward sustainable technology, because in some ways this can be a cheaper way to address the energy use than just building a lot more solar or a lot more wind or whatever it might be to try and feed an inefficient vehicle base. And I think over time, what people are going to find is that this efficiency change is what will drive adoption even faster. Today, electric vehicles are driven and plug-in vehicles are driven mainly by environmental concerns. People are well-educated, very thoughtful consumers that want to make a difference with their spending dollars, but they're typically not doing a detailed cost-benefit payback and trying to calculate how many dollars they'll save on a gallon, gallons of oil and operating cost. In the future, I think that you'll start to see more and more of that happening. And today we're actually very close to a tipping point, especially with the price of gasoline where it is in the recent weeks, where you can do a cost-benefit analysis and show that it's actually cheaper to drive a plug-in vehicle than it is to drive a gasoline vehicle. And it's going to take a while for people and consumers to start thinking in those terms. It's going to require some education and change of thought process, because it's looking at total cost of ownership and a longer life cycle than just the upfront cost. But that ultimately is what I think is going to drive adoption much, much faster. And this kind of defines how nasty that problem is and how tricky the problem is with transportation coupled to petroleum use. And you can see that today 96% of our transportation energy comes from petroleum. And that's all transportation, not just cars. That's airplanes, trains, trucks, buses, every single thing that's used to move a person or piece of cargo around the world. And of that, about almost all of it essentially goes into cars, trucks, and airplanes. And I can assure you that it's a lot harder to make an electric airplane to fly across the ocean than it is to make an electric commuter vehicle. So that is really where we need to attack this problem first. And I think when viewed from 50 or 60 years in the future, it's just going to look like a complete travesty that we were burning up all this cheap oil, driving 30, 20, 40 miles to work. When people are having to pay ridiculous amounts to use the oil that we'll still need in some cases to fly, in long trips and to go on intercontinental travel. So, and there's a reason oil is so dominant here. It's not just an accident, and it's not just because there's some conspiracy to burn oil, but it's an incredibly good energy carrier. It's very energy dense. You can see gasoline. This is a graph of just generally how much energy per mass there is in this fuel. And gasoline is almost off the chart. At the bottom here are batteries. Those are all different types of batteries. And there's one thing working in our favor here, which is that it's thermodynamically a little hard to get mechanical energy out of gasoline. So when you take into account that conversion, downgrade essentially, it's about an 80% downgrade. In a vehicle, you get a little closer to competitive, but still, gasoline has a huge benefit. And you can kind of zoom in here a little bit further, and if you remember, gasoline is still usable up at about 2,000. So we're still working with something like a 5-to-1 or 10-to-1 handicap in energy density. So it requires some really clever engineering and some design compromises to make that work. This is where you can kind of start to see the whole world of batteries today. And this encompasses all the different types and chemistries and all the different startups and ideas people are working with today. It's pretty broad. Going from lead acid to nickel cadmium to nickel metal hydride, you can kind of see the evolution in energy density. And today, lithium ion is a very broad family. There's a lot of different chemistries there. We focus almost entirely in that little box. So we spend a lot of time researching all the different vendors and makes and models and ways that we can extract better energy and better power out of these cells. Typically, higher energy density is the key here, and that's what's going to be, I think, the roadmap for improvements in vehicles. We see this growing at about 8% per year, and that's been true for quite a few decades. It doesn't seem dramatic. It's kind of a sluggish example of Moore's law, but if you run that out over a longer time period, you get a doubling in 10 years. And that's pretty meaningful, especially on something that weighs hundreds of kilograms in a car. It's almost as if you had like the material properties of steel changing at 8% per year. You'd build a very different vehicle 10 years from now if steel was twice as strong. And that's kind of what happens with batteries. You can build a very different type of vehicle if your batteries are twice as energy dense. And that is fundamentally what you see in a difference between a Roadster and 0 to 60 in 4 seconds or 3.7, 250 miles versus a previous generation of cars that might have had 100 or 120 miles of range and a lot heavier battery pack. So that's kind of the march of energy density that we've been on in the last few years. And since we introduced the Roadster, we've seen improvements of about 40% in our battery pack energy density. And that falls right in line with this 8% per year. Some of that is innovation that we're doing on cooling and packaging. Others, other benefits come from the cell level, chemistry innovations. And it's not just batteries. There's also an enormous amount of work that has to happen on power electronics and motors. However, batteries are the biggest lever. If there's one single thing that I kind of had an ability to impact dramatically, it would be battery technology. And I'd really want that to improve for the biggest bang for the buck. And cost of batteries is probably the single biggest factor, even within batteries. So, there's a lot of interesting challenges here and many different things to work on in research. Batteries are still the biggest lever. You can kind of get a sense of how the improvements are going. Power electronics are actually improving faster than batteries. It's pretty amazing how fast efficiency and power density are getting better on these power electronics converters, drive inverters, charging systems, things like that. But they don't have quite as big of impact on the overall vehicle. You could double the efficiency of an inverter or cut the size in half, and it wouldn't look very different at the overall specs you'd see at the vehicle, even though every 0.1% helps here. And just a few final comments. I wanted to talk a little bit about how electric vehicles integrate to the grid, because it's somewhat of a different technology where there's a synergistic relationship with the utility grid. And we can't sort of stand alone. All the energy to drive the car had to get made by electric utilities or power plants. So that tie-in and how those work together is very important. And we've had kind of the benefit of having the Roadster fleet around the world and around the country as a really interesting experiment on how this all works. And there's some fascinating data coming out of that. This is a graph of basically the different currents and voltages that we see Roadster owners charging at. And it was actually a little surprising to us because we spent a lot of time building this car that could charge pretty fast, had 70 amps at 240 volts of onboard charge power, so almost 18 kilowatts of onboard charge power. That wasn't easy to do. And yet we see only a tiny, well, out there in the far right, only a tiny amount of people actually taking advantage of that. And a lot of the challenge is the infrastructure cost. It's expensive to put in that kind of connection in your garage. Meanwhile, we see this huge peak down here. So what's going on down here? This is 120 volts at 12 amps. That is the standard 120 volt outlet that you see sitting on the corner of every wall. And we did take great pains to make sure the car could basically be a universal electricity converter. So the charger can take in 120 volts, and it does it pretty efficiently. But we never expected that you'd see something like 20% or 22% of all the energy used to power the entire vehicle fleet over this sample, which is 2 million miles, almost 800 megawatt hours of energy input, would be coming at 120 volts at 12 amps. And it's an interesting sort of experiment, but I think what this points to is that a lot of people just plan to charge overnight. They'll take advantage of that charging at the nighttime rates, and fast charging is interesting, but it's not as helpful or not as useful once you have a garage and the car lives at home. And just one final thought on this. This is kind of the time version of that graph. So looking at when did people charge. And this is the basically unmanaged version of this. We have not tried to do demand-side management directly. We have timers in the car, and people can configure and set this as they see fit. But this is something this was kind of the natural usage pattern. And you can see it's not perfect. This red graph is the California ISO load curve. This is back in 2009, but it hasn't shifted too much. And the blue are sort of these, basically the Tesla vehicle demand curve, if you want to think of it that way. So you can see that our demand curve was peaking at about 10 at night or something like that. That's generally, you can see more as people come home, they kind of plug in, the cars start to charge, and that's sort of how that looks. So ideally, what we would like to do is shift this to the right about 3 or 4 hours. And that's entirely easy to do because you can also see that all the cars are done charging by 4 or 3 a.m. So they basically finished charging at 2 or 3 a.m. and then sat there for 3 or 4 hours. So what you'd really like is to have them start charging at about midnight and then finish early morning. So that's another piece of innovation that we're working a little bit on, but also there's a lot of interesting startups and ideas that can help on that. So I think I'm a little over time, but I'll wrap up with one final thought, which is kind of this neat synergy between photovoltaics and electric vehicles. To me, it's kind of auspicious that you've got this interesting match of the amount of area it takes to cover up one car, which is about the amount of solar panels that you need to power a car for a year of average driving. It's kind of just lucky that works out that way, but it's neat, and one of those sort of fun physics facts. And we'd see a lot of customers actually adopting photovoltaics. It's a huge driver. We don't do it directly, but customers that buy EVs typically think about energy use a lot more carefully and then want to convert to solar use. So I'll wrap up with that and I guess turn it back over for questions.
That's good. Thanks.